January 19th. This is our second vodcast for thermodynamics, and today we are going to finish chapter 1. We're going to talk about pressure and measurement of pressure, which is called manometry. So before that, we have a homework assignment from the first 21 pages of chapter 1, and I would like to take a minute to see if anybody has any questions about the homework. Yes, Mr. Legursky.
So on number 11.
Number 11.
It asks you to convert from kilojoules per kilograms
Degrees Celsius. Uh-huh.
When you do the temperature conversions, how do you do that?
Oh, okay, great. Great question. Now, the first thing is, if you convert from a degree C to a degree Kelvin, to a Kelvin, it's the same because the span is the same. All right? So if you're converting, like on the first part where it says 1.005 kilojoules, I'm gonna flip this over to the document cam. Hang on a second. All right, so number 11. I don't know if we can see that or not. Let me see if I can come in a little bit wider. There we go. All right, so for the first one where we're in kilojoules per kilogram degree C, I'm going to ask us to convert to kilojoules per kilogram Kelvin. The number is exactly the same. All right. Now that only works if it's a delta. You know, it doesn't work. You have to change it. Like later on we start talking about a property called entropy, which is divided by T. The T has to be in absolute degrees. So, but the span of a degree Celsius is the same as the span of a degree Fahrenheit. So then on another one here, let's take a look at this. We're going to convert to BTU per pound mass degree Fahrenheit. Okay, so what we're going to do then, I'm going to widen this out a little bit. And we're going to start with our value, which we can't see right here. Okay, we're going to start with our value of 1.005 kilojoules per kilogram degree Celsius, and we want to change that into BTU per pound mass degree Fahrenheit. Okay, so we actually have three separate units. We need to convert kilojoules to BTUs, and we need to convert kilograms to pounds of mass, and then we need to convert degrees C to degrees F. All right. If you go back to the original temperature scales, on Celsius, you go from 0 to 100, and the same span on Fahrenheit is 212 to 32. So in other words, it takes 100 degrees Celsius to go this minus this, which is 180 degrees Fahrenheit, doesn't it? So what that means is, if you say 100 degrees Celsius per 180 degrees Fahrenheit, and if you look at that, that cancels to 1 over 1.8, which is actually 5 over 9. So it's 5 over 9 degrees C per degree F. So far, so good? Yeah. So when you do the temperature part, you have Celsius in the bottom, so you multiply that by, and then that will cancel, and you've converted your denominator. Oops, it's not very good. There we go. Right? Is that helpful?
Yeah.
Great. Other questions? All right. Well, that's a really good question, and I appreciate that. And any questions that you have, if you bring them to class like this, we can clear it up and make it a lot easier on you, and also just make sure that we're all operating in the same dimensions. So that'll work. I don't mean dimensions literally. I mean that we're all on the same page. So, all right. So the next thing that we're going to talk about in this class is the idea of pressure. And it actually turns out that I am missing a page of my textbook. I'm missing 2 pages. and it's not even a front and a back. It's like when I photocopied this, 22 and 23 just didn't get copied, so I have 24 on the back of 21. So some of this is going to be a little broad, considering your textbook. But here's the basic idea. Pressure is measured in dimensions of force per area or force per length squared, right? And there are some different ideas of thinking about pressure, but we have atmospheric pressure, and we have gauge pressure, and we have absolute pressure, which is the sum of those two, right? So basically, let's think about some common pressure measurements. If you watch the weather, you'll see that the atmospheric pressure is often measured in inches of mercury, or if you have your blood pressure taken, it's actually measured in millimeters of mercury, which are fluid conversions, but they also speak to the way that pressure is measured with an instrument called a manometer, which you'll understand by the end of the day. And the process of doing this is called manometry. Although pressure is, the measurement of pressure is always called manometry, even if you're not using fluid-filled columns, although that's sort of the basis of where it came from. Atmospheric pressure is the pressure that's exerted all around us, and it's basically the weight, which is a force, of a column of atmosphere. And what does that mean? Well, if you're standing on the Earth, okay, this is you. Maybe it looks like you're up in Iceland, which would be fun. But basically, the Earth's atmosphere is quite long, and it exerts a force on your body in much the same way that if you are swimming, if you're diving, say that you get to go snorkeling, not in Iceland, but you're down here in the Bahamas and you get to go snorkeling, there's going to be a column of water exerted above you, and so you're going to feel the pressure from, you're not dead, you're just snorkeling. There you go. So there's your mask. So you have this column of water exerted above you, and this is why people who dive actually have a great deal of pressure put on the body, and it can change you. It can do some physiological changes, and so you have to decompress slowly, which otherwise you get the bends, which is just a reaction to blood gases evolving too quickly based on differential vapor pressures. However, we don't feel that when we are in the atmosphere because it's just all around us. But there is an atmospheric pressure, and the atmospheric pressure changes based on weather conditions and also our location. So, for example, here in Powell, Wyoming, we're at an altitude of about 4,500 feet. And that means that, although it seems odd, if you're talking about going to Los Angeles, and my basic feeling would be to say Los Angeles is that way, right? But it's really not. It's really that way because it's down nearly a mile from where we are. What that means is that if you were in LA, you are actually farther down in atmosphere, and there's actually a longer or taller column of atmosphere pushing on you when you're in LA than when you are here. So, Carter, what is the elevation in Laramie, Wyoming?
7,200.
Very good. Yeah, it's very, very high. So, what happens to athletes when they go to Laramie when they're used to being at sea level?
You're out of breath.
Yes, they're out of breath because they're just not as used to breathing the rarefied air that people are in Laramie. So anyway, what does that mean? Well, it means that atmospheric pressure is actually less in Powell, Wyoming, or in Laramie, Wyoming, right, which is another 3,000 feet or 2,500 feet higher than us, compared to at sea level. So when they report atmospheric pressure, this is what they're talking about. Although, oddly enough, when they report it on the news, they correct it. So they don't report what the atmospheric pressure actually is here. They report what it would be here if we were at sea level. And the reason that they do that on the Weather Channel is because they want to explain weather phenomena, and weather moves according to low pressure, high pressure regions move into low pressure regions. That's why a low pressure region on the Weather Channel indicates that weather's coming in. High pressure region means the weather's stable. And that's actually what's happened here in the Bighorn Basin in the past couple weeks. It's a little bit different. We have this feature called the temperature inversion, which happens because we're ringed by mountains. So do you guys know right now, has the temperature in the basin been warmer or colder than the surrounding area recently? It's colder, okay? And I know this, I was in Cheyenne last weekend and it was 8 below here and it was 37 degrees in Cheyenne. And Cheyenne is not like the banana belt, right? But it's 40 plus degrees higher in Cheyenne. Well, the reason is, which is heavier, cold air or warm air? Cold air, it's more dense. So what happens is when you have a ring of mountains, when the cold air settles in, something has to move it out. You have to have a wind to blow it out. So if you don't have a low pressure region, it will stay there for a long time, and that's referred to as a temperature inversion. In mountain valleys, you can't really see it here because the basin is too large, but if you ever go to a mountain valley, like Jessica being a Colorado person, you've probably seen this. You can actually go into a basin and see it. The air in a tight mountain valley will actually get almost a foggy look to it, and it's just heavier. Yeah, it's really pretty. It's kind of an elegant look, but it's kind of a strange thing just the same. So anyway, what we're getting at here then is pressure is a funny thing. However, atmospheric pressure is just what's going on all around us. So if I took a pressure gauge, like a tire gauge, and I just held it up in the atmosphere like this, it would register 0, wouldn't it? It doesn't mean that there's no pressure. What it means is the pressure is the same on both sides of the gauge. And so you can't feel it because it's just like all around you. So we have to measure atmospheric pressure with something that is both closed to the atmosphere and open to the atmosphere. And that instrument is called a barometer. And in the old days, back before people were really aware of how potently toxic mercury was, the way that a barometer worked was they would invert an evacuated glass tube into a mercury bath. Doesn't that sound nice? So we'd have a mercury bath. The atmosphere would press down on the mercury, and it would drive the mercury up into the tube. Now, when mercury is driven up into the tube, it forms a column that is curved, and the curve on a column is referred to as a meniscus. Some fluids form an upward-facing meniscus. Others form a downward-facing meniscus, depending on some of the fluid properties. We won't talk too much about them, but mercury forms an upward-facing meniscus. And the further up it goes, what do you think it's saying about the atmospheric pressure? Since the tube is evacuated, it's not exposed to the atmosphere. The further up the column goes, do you think that means the atmospheric pressure is higher or lower? It's higher as it goes up, yeah, because it's pushing down harder, making it come up into the tube more. So if you have a lower atmospheric pressure, the height of that mercury column will be less. Okay, and so this is back in the old days how they measured barometric pressure. Mercury is a great gauging fluid because of a couple of properties that it has. Aside from toxicity, what kind of property does mercury have that you think might make it a good fluid to put into a gauge? Or even how is mercury different from water? Yes?
It's kind of like a solid because it rises itself.
Yes. That property is called surface tension. And mercury prefers to adhere to itself. That's why the meniscus is curved upward. Mercury has more of an affinity for adhering to other molecules of mercury than it does to adhering to the glass. So what happens then is mercury goes up and down. It stays together rather than like vaporizing and sticking to the glass. You know, so that can be a problem when you're trying to gauge something. What else do you know about mercury?
It's like a liquid, so you can put it in smaller plastics.
Like capillaries? Yes. What about the weight of mercury compared to the weight of water? Heavy, that's right. It is 13.6 times the weight of water, the density of water. Which means that to get this effect with water, except for the, and excluding the surface tension, the vapor pressure effects and so forth, to get this effect with water, to measure the same amount of pressure, atmospheric pressure, you would need a column of water 13.6 times as high. So if you needed this much mercury, you would need to the ceiling of water to get the same measurement effect. So you can make things relatively compact. It's not to dismiss the toxic properties of mercury, so don't play with mercury. They used to play with mercury all the time, they just didn't know. Because it's really cool. Mercury is, really fascinating stuff. But the other part of the good news, though, is like if you break mercury, if you have an old-fashioned mercury thermometer, if you break it, it just balls up because of that property of the desire to adhere to itself rather than adhere to the surface of anything else. So it's kind of easy to pick up or vacuum up, so it doesn't make a mess. There are some significant cases where mercury becomes volatilized or gets messed up with stuff, and if it gets hot, you can vaporize it, and if you're around it a lot. So that's why back in the old days, apparently, men's and women's hats were made out of felt, and they used to block them with mercury. And they used to say that people who worked with hats were crazy. And so the expression was mad hatter or mad as a hatter. And that's where that came from. And they didn't really know why. But people have used mercury for all kinds of weird things. There was a case up in Montana. This was many, many years ago. But there was a guy who was testing equipment for the Montana Power Company back in the 70s. And he just started to develop weird symptoms and kind of just had dementia and some liver problems. And they found out that he was suffering from mercury toxicity, and they really couldn't figure out why. But what had happened was they found out after he passed away, they took his company truck and they ripped up the carpet. And apparently he had just over the course of many years, had thrown mercury gauges into the passenger side footwell of his pickup, and the whole carpet was just saturated with mercury. So every time he kicked on the heater, he was just getting hours of face full of mercury vapor. So bad thing. So be careful with mercury. Don't breathe it in. It's not good for you. Anyway, so this is how getting atmospheric pressure works. Now, we also talk about gauge pressure. And gauge pressure, one of the best examples I can think of is, like I said, with a tire gauge. You have a little end that you can just put onto your tire stem, and it just inflates a gauge to indicate where the pressure equalizes. That pressure is called gauge pressure because you read it off of a gauge. So the difference is that gauge pressure does not include atmospheric pressure. All right, and last but not least, absolute is atmospheric pressure plus gauge pressure. Now, gauge pressure can be negative, which indicates a vacuum. So if you have a negative gauge pressure, it just means that you're operating in a vacuum. Now, the interesting thing about that is atmospheric pressure and absolute pressure can never be negative. Doesn't make any sense. If we did everything, we'd get whooshed to wherever it wasn't negative anymore. So even in deep space, absolute pressure will be close to zero, but it's never below zero. So if you have a gauge pressure that's negative, meaning that you're pulling a vacuum on something, to find the absolute pressure, the value of this gauge would be negative, wouldn't it? So that means in the case of a vacuum, absolute pressure can be below atmospheric pressure, but it can never be less than zero. So the only thing that can be less than zero is gauge.
How
Yes?
do you, like depth
Yeah.
meters and like altitude meters,
Yeah.
how do they work?
You, like on the standard atmospheres, or?
Yeah.
Oh,
Because like when you're underwater,
right.
you're not exposed to the atmosphere.
Well, that's a good point, and let's talk about that, because that actually is a great, see, you guys are great. That's a great segue into the next, how we measure pressure and what pressure is measured. So we're going to go scuba diving again, okay? So if you are underwater, the symbol for a fluid in contact with the atmosphere is a little triangle like that. So this just means this is my surface, this is my swimming pool or whatever. And if I'm down here, scuba diving, okay, I have a column not of air, but of water above me, right? I also have atmospheric pressure above me. So in other words, but the pressure that I'm going to experience at this depth is going to be the pressure of the atmosphere plus the pressure exerted on me by the weight of the fluid column. Now, if the density of the fluid is constant, which is not always is, but water for the most part, the density is constant, then the pressure due to the fluid column is equal to that density times gravity times the height of the fluid column. Okay? So the pressure that's exerted on me at depth then would be rho g h. All right? Now, it's actually a differential equation. In other words, if pressure changes with depth, as it sometimes will, sometimes if you have a compressible fluid, as you go farther, it actually gets heavier under its own weight. Okay? Or if you had very dirty water, a lot of turbidity, the dirt and particulate matter was settled to the bottom, so it would be more dense at the bottom than it will be at the top. Okay? But overall, this is a good place to start. So if the density is constant, if you don't have any of the compressional or differential settling effects, then you have something like that. Another thing I guess I could say, like if you have a column of fluid, what if you had two columns of fluid? Like, have you guys ever looked at like oil and vinegar dressing, salad dressing? It separates, right? So what's on top? The oil, because oil's lighter, has a little smaller density than vinegar, so it floats up to the top. Same thing used to happen with milk. Like if any of you have ever been to a farm and you get milk from a cow directly, it's not homogenized. Homogenized means the cream is stirred in a very small way. Milk is really interesting, by the way. I won't get into it too much because I mean it's kind of one of those things. But milk is a fascinating. It's called a colloidal suspension, and there's a lot of cool properties in it. However, the cream will float on the top because the cream is lighter than the rest of the milk. So in normal life, you actually get cream and skim milk. You don't really get 2% or 4%. That's modern living. So there you go. So you get a little blue milk, and you get a little cream, and make butter and put cream in your coffee, which I think is disgusting, but there you go. So anyway, coffee is just fabulous all by itself. So anyway, so you can tell what the depth of this is based on the height of that fluid column and the density of the fluid. Now, this is kind of an interesting thing as well. The density of water, and we always talk about water because water is unbelievably cool. Water weighs 1 gram per cubic centimeter, right? Or in English units, it weighs 62.4 pounds per cubic foot. That's pure water. So do you think that salt water is more dense or less dense than distilled water or pure water? Yeah, it's more dense, exactly. The salt dissolves. So what that means is, if any of you have ever been swimming in the ocean, it's easier to swim in the ocean because you float better. People float yeah, see, there's California boy says, yep, that's right. You float a lot better in the ocean. It's also interesting, the density of water, pure water, is very close to the density of muscle and bone. And so most adults, because fat is less dense, even if you're a very thin adult, most adults are less dense than water, so we float. But every now and then you'll see a scrawny little kid I had one, my oldest son was a scrawny little kid, and he sunk. And so every now and then you'll see a kid that seriously cannot swim. So you just have to get a little bit older, get a little bit more body fat, and then they can swim. But it's kind of an interesting effect. So even people who are even little scrawny kids can probably swim well in the ocean because the ocean is more dense, or in salt water in general. So that's kind of a fun thing. And little kids that can't swim in a swimming pool get really excited by that because it's a big deal. All right, so we've talked about atmospheric pressure, gauge pressure, and absolute pressure. I've also not really addressed this physically very much, but the reason that you can never have a pressure, an atmospheric pressure of 0, is if you think about it just from a point of view of force, you always have to pull against something. So if you have a pressure that's less than atmospheric, it's going to continue pulling. You know, you're going to pull something until the pressure equalizes. So there's no such thing as a perfect vacuum. Space is a very good vacuum, but it's not perfect. And vacuum pumps and so forth can create very, very low pressures. However, total 0, not possible. There are some other effects that occur when you start pulling low pressures. You start to vaporize or evolve gas out of fluids, and so you can change into sort of a multi-component system or a 2 or 3 phase system, which is another interesting thing. But basically for now, all you really need to know is that atmospheric pressure is always going to be greater than, could technically be equal to 0. Gauge pressure can have a low value of whatever the atmospheric pressure is, up to any kind of a high value, really, depending on a lot of different things. And then absolute pressure, of course, always is going to be greater than or equal to 0 as well. Right? So, manometry. We talked about barometers. We talked about how barometers act. And we've also talked about this idea. We've talked about it in 2 different ways. Pressure, which has dimensions of force per area, or force per length squared, can be expressed as rho GH. In other words, the density of a fluid times the gravitational acceleration times the height of that fluid column. If you break this down dimensionally, density is in units of mass per length to the third. Gravity, if you remember, weight is equal to mass times gravity. So one way you can think about gravity is being a weight over a mass. It's other things as well, but if you just do the dimensions, you can see that. So gravity would be weight over mass. And then height, of course, is in length. So masses cancel. This length cancels one of these, and we're left with weight per length squared, which is dimensionally equivalent to force per length squared. But it also shows that since it's involved in height, you can report pressure, and this is a complete throwback to mechanical engineering systems in measuring pressure as a function of a height of a fluid column. So you can report pressure as length or height of a particular fluid. Height of whatever the fluid is. Height of a mercury column, height of a water column, height of an air column. And boilers, if you ever have a chance to go into an old building and look at an old-fashioned boiler, the gauges are generally recorded in inches of water, which is kind of interesting. I think last time I was talking about my multi-fuel stove, not the multi-fuel stove that I have now, but we used to have just like a Blaze King or something. I was talking about the draft on a chimney, which draft is a differential in pressure, isn't it? Because you want your smoke to go up and out of your house. So you want to have a draft, which means that you want the pressure at the top of the chimney to be less than the pressure at the bottom of the chimney. Otherwise, you have to mess around with your dampener, which is never a good idea. So the best way to get pressure differential in a chimney is to have a big wide chimney that goes straight up through your roof. Anytime it kinks around, like sometimes it'll come off the back of the stove and have to go up, or you have to put it through a wall and it goes up. Anytime you have a kink like that, you have a chance of backdrafting. But the best kind of chimney comes right out the top of your stove, goes straight up in a big 8-inch or 6-inch hole. So when we were installing one stove, it requested a draft in inches of air. So my husband and I converted inches of air into some other units and found out that basically it was very tiny, and ours was like, sounded like a freight train was going up through the ceiling. So that was a good indication that we had enough draft. But pressures reported in a whole bunch of different units for a whole bunch of different ways. So if you have your blood pressure taken and they tell you that your blood pressure is at 120/80, what that means is they heard the first heartbeat at 120 inches or millimeters of mercury. It's millimeters of mercury. And the reason is, if you look at the old-fashioned blood pressure machine, if you go to your doctor's office, it's hanging on the wall. It's a gauge with a mercury column in it. Anyone know what a blood pressure machine is called? It's called a sphygmomanometer, or I'm sure I'm mispronouncing it, but that's how it's spelled. So, so all of this comes out from gauging, which gauging just means measuring of pressure. Okay, so you can measure it in a height of a fluid column. You can measure it in units of force per area, force per length squared, which in the United States we would measure in pounds of force per inches squared, which we call pound per square inch, or PSI. A PSI is quite tiny, so we also measure in thousands of pounds of force per inch squared, which is called, 1,000 is abbreviated K, so we call that a KSI. If you want an even tinier unit, you can measure in pounds of force per feet squared, which is called a P, pound per square foot, PSF. So what do you suppose 1,000 pounds per square feet is called? Go ahead and say it.
KSF.
Yes, KSF. So those are the units that we use commonly in the U.S. customary system. In the SI system, the force is measured in newtons, and the area is measured in meters squared. That unit is called a Pascal, named after Blaise Pascal, who was a famous mathematician. That is a way tiny unit, because a cubic meter or a square meter is huge. A meter is a foot, and a newton is a little bit of it. It's like a quarter of a pound or something like that. So basically, you're talking about almost no pressure. So we also gin that up, and we measure things in kilopascals, which is 1,000 of those, megapascals, which is 1,000,000 of those. Okay, so typical, just to get you a scale or an idea of what sizes we're talking about. 1 atmosphere of pressure. That means standard atmospheric pressure at sea level. We can also call it 1 atmosphere. You may remember from chemistry, they measure, for example, the universal gas constant, liter atmospheres per mole degree Kelvin. So an atmosphere is the same as about 14.7 psi, is the same as about 101,000 pascals, or 101 kPa, kilopascals. Okay, so you can see how tiny a Pascal is. There's a zillion other measurements for pressure. Oh my gosh, they are just all over the place. But they all come down to these sorts of ideas. Okay? All right, so let's take a look at a problem like this. Figure 155 in your tech 1-55. If you wish to measure the gas in a container, in any sort of a thing that is contained, you want to measure the pressure of that gas. The type of implement that they're using here, the instrument they're using here, is called a manometer. Once again, manometry refers to the measurement of pressure, so manometer is used to measure the pressure of gas. Well, we use a couple of principles when we use manometers, and we sometimes use different gauging fluids because of their densities and their relative properties with each other. But basically, if we have some sort of a gauging fluid, like let's say we have mercury in this tube. Does it make sense to you that if we're open to the atmosphere, this point in the mercury is going to have the same pressure as the atmosphere? In other words, because what would happen if it didn't? What happens if the pressure in the atmosphere was less? What would the mercury do? It'd follow it, wouldn't it? So by definition, once we draw the picture, we're saying it's stabilized, it's at equilibrium. Those two pressures are the same. So what that means for us here is that if this is mercury, right here, pressure, this is the pressure of the atmosphere because it's open to the atmosphere. All right, so as we go down in the fluid from what we've learned, do you think the pressure at point 2 is higher or lower than the pressure of the atmosphere? It's higher, exactly, because we're farther down. Here we are, here's this little tiny, wee little scuba diver. And he's going to be experiencing a pressure that's equal to the pressure of the atmosphere plus rho GH, whatever this is my height, whatever the density of the gauging fluid is. All right, now when we come around the bottom of this U, the height here and the height here are the same. So the pressure here must be the same as the pressure at state 2, right? It's equality of pressure. Now, that would not be the same if we had two different fluids, but if we have the same fluid, we have a continuous loop of the fluid, and they're at the same elevation, they're going to be at the same pressure, right? Equality of pressure. So the pressure here, pressure at 1 is going to equal the pressure at 2. And then the pressure of a gas, because a gas is very light, meaning it has a very small density. The density is, let's say, approximately equal to 0. It's not really 0, but it's similar to 0. It's very small compared to the pressure or the density of a liquid. Also, because the pressure, the density of a gas is quite small, the pressure in the entire vessel is going to be similar. So in other words, you can say pressure of the gas. Pressure of the gas in the middle of the vessel is going to be similar to the pressure of the gas at the top of the vessel, similar at the bottom. So if we have a continuous arm of fluid of gas from here to here, and if that gas is very light, we can also say that that is very similar to the pressure of the gas. Okay? So that means if we know atmospheric pressure, and we know the height of this fluid column, and we know the density of this fluid column, we can use that principle to find the pressure of the gas. And that's how a manometer works. So when you have a manometer, you open it up to the atmosphere, usually, or you open it up to another ball of gas or whatever, and then you measure the height, and you know the density of the gauging fluid, and you can determine the pressure in the vessel. Similarly here, let's just look at this. Okay, now we need to talk about this idea. What does specific gravity mean? Specific gravity means the density of our fluid divided by the density of water. So it's a ratio. It's easy to report things in specific gravities because there's no units associated with it. As you're probably learning, the units associated with pressure measurement are a little strange. They go on and on. So if you say a fluid has a specific gravity of 0.85, all it means is it's 5% as heavy as water. So that means if water has a density of 1 gram per cubic centimeter, this fluid has a density of 0.85 grams per cubic centimeter, and so forth. You could take it, multiply it by the 62.4, and determine that in units of pounds per cubic foot. All right, so what's the pressure in this chamber if it's a gas? Well, the pressure of the gas here is going to be our atmospheric pressure, 96 kPa, plus, because we're going down, rho GH of the fluid. That's going to equal the pressure of the gas. So I have this value, and if I can figure this out and get it into units of kPa, I can also find the units of gas. So you probably know that's what I'm going to do right now. So if my density, I want to get this in units of kPa. Let's talk about units because it's always important. That means 1,000 Newton per meter squared. So that means I'd like to get my height in meters. I'd like to get G in a unit that is an SI unit, like 9.81 meters per second squared, or 9.81 newtons per kilogram. Same, they're dimensionally equivalent. And then I want to report my density in units that correspond to that as well. All right, so rho, let's go like this, specific gravity is equal to 0.85, which is equal to rho of my fluid divided by rho of water. And I want to get that in units that are going to correspond to kilograms, meters, and second. So the density of water, I told you, is 1 gram per cubic centimeter. And if I wanted to express that in kilograms per meter cubed, you can bet that that's just going to be a factor. It's going to be some multiple of 10, right? And it's actually 1,000. But let's go ahead. I'm just going to run this on. You can take a look at what we got going on the computer, how easy it is to find that data. And I can just type in density of water in kilograms per meter cubed, and it's 1,000, right? So that means that this is 1,000 kilograms per meter cubed. Since the specific gravity of my fluid is 0.85 times that, I see the density of my measuring fluid is 850 kilograms per meter cubed. Oops, you probably want the other page. Okay, so there we go. All right, so continuing with this idea then, rho GH is equal to 850 kilograms per meter cubed times G. Well, let's go over here. Weight is equal to mass times gravity. In the SI system, we know that G is 9.81 meters per second squared. But if you go back to Newton's second law, you can also see that weight per mass is equal to gravity. And in the metric system, weight is measured in newtons, mass is measured in kilograms. So I can also say that G is equal to 9.81 newtons per kilogram. Those are dimensionally equivalent. So I take my rho, multiply it by 9.81 newtons per kilogram, and multiply it by the height of my column, which is 55 centimeters. Need to report that in meters, 0.55 meters. And I can see from my units that I'm going to get Newton per meter squared. And my value is 850 times 9.81 times 0.55. 850 times 9.81 times 0.55, and that value is 4586.175. Okay, Newton per meter is a Pascal. So if I want to report that in kilopascals, I would say 4.59. That would be thousands of Newton per meter squared, which is kilopascal. So that means that the depth of this fluid column, or the difference in height of this fluid column, represents a picture of 4.59 kPa greater than atmospheric pressure. So my pressure of the gas is equal to the atmospheric pressure, which is 96 kPa, plus the gauge pressure, 4.59 kPa. And so the total value is 96/100.6 roughly kPa. Okay. All right, now sometimes you will have when you do your homework, you'll see that you may have a multi-fluid manometer, but this is really how it works every single time. If you have a column of fluid that goes down, the pressure increases. If you have a second fluid and the column goes up, the pressure increases. Always rho GH, okay? But so if you have something like this problem, okay, open to the atmosphere, we go down to H2. This is the same fluid, or we go down H3, sorry. We come up H2. So if you start with atmospheric, you add rho GH, and then you subtract this rho GH. To here. So this is mercury, so that's very heavy. This is oil. And then the pressure in the water tank. This is not a gas, so we cannot say that the pressure here equals the pressure here. We have another height difference to get to here. So we went up, H1, so that's minus rho GH again, and that's going to equal the pressure of air in the top of the tank. Okay. So that's the two ideas you use every time you have an interface. The pressure is equal on both sides of the interface. Column of fluid increases the pressure going down and decreases the pressure going up. And I guess the third idea is that if you have a continuous fluid at the same level, if it goes around to U, either up or down, but if they're at the same level, they're going to have the same pressure. All right. You guys have any questions for me at this point? You're going to have more fun when you get into the homework. So on Tuesday, I would like you to bring any questions that you have about the homework, and we'll answer them in class. And then we'll begin on Chapter 2. But make sure that you have your homework of Chapter 1 as done as you can on Tuesday so that we can ask questions and then get on to Chapter 2. The other thing in Chapter 1, I'm not going to really go into it with you, but they talk a little bit about significant figures. And I'm not a real stickler for significant figures, but I hate to see something like if you have 4.2 times 1.7, I hate to see it with 7,000 decimal places. So keep it in the ballpark of how it was measured, okay? All right, no questions for me? All right, well, have a wonderful day, and we will see you Tuesday to finish answering questions about Chapter 1 and begin Chapter 2. All right? And I'm going to stop the podcast, so we'll see you guys next time.